want to warm up for math, like maybe you're going to do the 10 a week, keep in mind your quiz this week is going to be on 1.5 and anything else we learned this week. Okay, so you got to stay on top of things. Okay, what we're going to learn is we're going to learn about quadratic functions. Now, quadratic functions are actually part of the polynomial function family. So there's a whole family of functions that have natural numbered exponents. When I say a natural number, guys, what are natural numbers? Whole numbers actually start with the whole. They start with 0. Okay? So whole numbers include 0. So it's 0, 1, 2, 3, 4, 5. So they start with the whole. Natural numbers are your natural counting numbers. So where do you naturally start counting? 1, 2, 3, 4, right? So if I say natural numbered exponents, okay? So quadratic functions are part of the polynomial family. And part of polynomial functions would include linear functions. So that was like your y equals mx plus b. And then we're going to have quadratic functions. And these ones are going to look like this: ax squared plus bx plus c. When you think of a polynomial function, I need you to think exponents are natural numbers. So when you're thinking about the exponents, you're thinking like, okay, well, what are your natural numbers? 1, 2, 3, 4, 5, and they go on. So when you're part of the polynomial function family, linear functions are a part of that. The exponent on the variable x for a linear function is actually a 1. So it's a natural number 1. If there's nothing there, it's assumed to be 1. So linear functions are part of the polynomial family. Quadratic functions are also part of the polynomial family. And then in grade 12, whether it's 30-1 or 30-2, you're going to do cubic functions, quartic functions, quintic functions. So in grade 10, we do linear functions. In grade 11, we do quadratic functions. And then if you're in math 30-2, you get 4 polynomial functions: the constant, the linear, the quadratic, the cubic. If you're in math 30-1, you get 6 polynomial functions: the constant, the linear, the quadratic, the cubic, the quartic, the quintic. Okay? So it goes from like 1 in each grade to like, hey, here's 6, right? And you're going to have to know what makes them a polynomial function. And just the exponents on the variable x would be considered natural numbers. Okay? So what we're going to do is we're going to be talking about something called vertex form. And you guys have no idea what a vertex is, and I'm going to show you what a vertex is in a minute. Okay. Whenever you're graphing a quadratic, okay, you need to know that there's going to be critical features that must be accurately graphed. Chapter 3 and 4 is going to be all about doing the algebra necessary to find x-intercepts, y-intercepts, and the vertex. The vertex is a turning point on a quadratic function. Okay, so I'll show you what that looks like. When you guys were in elementary school, you guys did a lot of tables of values, and you guys would get your ordered pairs from your table of values. Okay? If I did this, -3, if x was -3, and if I'm graphing a quadratic, then f of x, okay, so f of -3, this is how you use the x value as being inserted into f of x. And this would be -3 squared. Guys, what's -3 squared? +9. When you square a negative number, it comes out positive, yeah? Okay, if x was -2, then f of -2, using function notation, would be -2 squared. Guys, what's -2 squared? 4. So then we've got -2 and 4, and I'm just randomly choosing any x value. I could have said x was -10, but it wouldn't fit on my grid, right? I could have said x was -15, but it wouldn't have fit on my grid. So I'm just choosing some reasonable x values that are going to take us from quadrant 1, quadrant 2, potentially quadrant 3, and potentially quadrant 4. Okay? So if I said my x value is -1, then f of -1, this is just function notation in action. We get -1 and +1. If x was 0, what's y? What's 0 squared? 0. 1. What's 1 squared? 1. Like, your brain here should be thinking, oh, okay, if y is equal to x squared, then 1 squared would be 1. Here, your y is equal to 2 squared, which gives you 4. Now, you're going to notice that I'm going to be using function notation more and more when I'm describing ordered pairs, because we need to. We're going to have multiple functions on the same grid. If you were to graph this function, -3 and 9 is just not going to fit. It's way up in quadrant 2 and it's too high. But I'm going to start at -2 and 4, -1 and 1, 0 and 0, 1 and 1, and then 2 and 4. So what you need to know is you need to know how to use the equation that's been given to give you a table of values. Why? Because calculus, there's no calculator, right? So if you're going to be on that road, so I've come up with some ordered pairs. Now all I want you, this was just grade 12. All I want you guys to do right now is in your graphing calculator, we're going to graph the most basic quadratic. So by definition, a quadratic has a natural numbered exponent on the variable x. Do you guys see a natural number on the variable x? That's a 2. That's a natural number. So when I take a look at my graph, there it is. Okay? And we can look at the table of values. Second function table. Your table of values always wants to start at 0. It's wrong. Never start at 0. We are not limited to positive x values. You always want to make sure when you're coming up with your table of values, you're going to grab a few negative x values, a few positive x values. Now, what you should notice is the y values are going up on either side of 0 and 0. Do you guys see that? So we can see that there's basically, at 0 and 0, we had a turning point. We are going down, and then we hit 0 and 0, and then we're going back up again. And every quadratic function is going to have a turning point. And that turning point is called the vertex. And that's a critical feature. So when you're graphing this function, okay, that's not a very good graph. I'm going to just try that again. This is f of x equals x squared. If you don't like that f of x notation, I need you guys just to call it y equals x squared. Now, a lot of people, by the time you get to like later, like in this course, you'd be like, oh, -3 squared is 9. -2 squared is 4. -1 squared is 1. And you could actually come up with these without doing this or typing it into your calculator. You're just thinking, I'm squaring the x value to get my y value. And then we end up with this parabola. Guys, what's my domain and range of this parabola? Are there any limits on the x? So if we say that the domain, if it can keep spreading out forever, then I'm going to say x such that x is an element of the real number system. Done. The range, do you guys see that the lowest value for y was 0? And we're going up from there? Okay. So the way we're going to write this is y such that y is greater than or equal to 0, comma, y is an element of the real number system. It's a continuous function, so we do have to say that it's YER. But the lowest point that we have for the y value is 0. This turning point, so right now, this is like going down, 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 down. It turns around and then it goes up. This turning point right here is called the vertex. Critical features of any graph would be x-intercepts, y-intercepts, and vertex. And this whole unit is going to be algebraically determining all three of them. Okay? So now what I want you guys to do, so notice I gave them different names, okay? We just did f of x is equal to x squared. Could you just come up with the table of values again and just see if you could do it in your head? Like if I had -2, -1, 0, 1, and 2, without looking at your calculator, can you use this number, square it to get the y value? Like, can you get that table of values? Okay, that's our base function when we haven't applied any other numbers. And this is going to be our original, this is your base function. There's no numbers attached to it. So this is f of x. And this is exactly why we want to start using function notation, is because on the same grid, I want you guys to graph g of x. And then on the same grid, I want you to graph h of x. So using your graphing technology, I want you to give me a table of values, and I want you to make sure your table of values has the lowest point on it. This parabola is going to be opening up, and it's going to have a minimum value, a minimum vertex. And I want you to graph this. So on your calculator, so this is your g of x. So there's my original function. Just do them one at a time. Don't put multiple functions on the same grid. Just do them one at a time, but on paper we're going to do 2. So if I have 2x squared, and I take a look at the graph, and I take a look at my table of values, so I see 82028. And I could see that this y value is my lowest y value. Does this 8 make sense to you? Okay, so let's think about this for a second. If I took order of operation dictates, if I square -2, what do I get? What's the square of -2? 4. What's 2 times 4? 8. So don't just expect your calculator to do the work for you. Your calculator is doing the work for you, but understand what the calculator is doing for you. Okay? So when I graph this function, how would you describe what did the 2 do to the shape of the parabola? Like using your words, like what would you say happened from the black function to the red function? Does the red function look skinnier? Okay, it does, so it appears thinner. And this is the language you're going to have to use from the description. So if I have this graph, and we put a 2 in front of it, we describe it as a vertical stretch by a factor of 2. So instead of saying, oh, the parabola got skinnier, we don't use that word. This distance that was 1 unit from the x-axis got doubled. This distance that was 4 units from the x-axis also got doubled. Do you see that this 4 turned into an 8? This 1 turned into a 2. You can't double 0. 0 times anything is still just 0. You guys get that? So you're going to learn like the super duper like language that goes with this. You would describe it as a vertical stretch by a factor of 2 from the x-axis. If it's on the x-axis, we can't pull it away from the x-axis because it's already sitting there. But if there's an ordered pair that was 2 units away from the x-axis, would then be 4 units away from the x-axis. So this is the language that we use to describe the a value that's attached by multiplication. Yes? Yeah. Totally wrong. I just put Zoom 6. Guys, if you've got a crazy window happening, like if your window is not the standard window, like if it doesn't look like this, you push Zoom 6 and it goes back to your standard window. So some of you guys might have some interesting things happening because you had like quadrant 1 only. Like I think that sometime during sequences in the series, we did a quadrant 1 graph only. Well, we need everything. So just Zoom 6 takes you back to your standard. Can I get you guys to please take h of x, put it on the same grid, but come up with the table of values associated with it. If you put a 1/2 in front of the x squared, what's the table of values that you end up getting? So if I was practicing my mental math skills, I'd take the -2 and I'd square it. What's -2 squared? 4. What's half times 4? 2. Okay, or you're typing it into your calculator. Okay, if you compare it to the original, okay, so I'll just do my original in black. So x squared. What happened? How would you describe the problem that took place here? Did you guys see that it got wider? So the 1/2 in front of the x squared. So what you guys did when you guys were in grade 10 is you guys analyzed all the critical features of a linear function. We have to analyze all the critical features of a quadratic function. So in this particular case, we ended up with like 0.5, 0, 0.5, and then 2. And when I graph this function, do you guys see that the vertical distance from the x-axis was half as much? So this is h of x in blue, and then this guy in red was g of x. When you compare it to this guy, the 4 was half as much. The 1 was half as much. The 0, anything multiplied by 0 doesn't change it. Half of 1 is a half. Half of 4 is 2. This distance is half as much. Do you guys see that? Making it appear wider. So the way we describe it for this guy, so from f of x, we would describe this as a vertical stretch by a factor of 1/2, and then we have to say from the x-axis. And the reason why we have to use this language really, there is no horizontal stretch in this course, but in 30-1 there's going to be a horizontal stretch. And we're going to be pulling from the y-axis. So what we're doing right now is we're actually either making it go closer to the x-axis or making it go further away from the x-axis. If it gets closer to the x-axis, it appears wider. If it gets further away from the x-axis, it appears narrower. Can you guys get that? Okay. So now, all I want you guys to do, quickly sketch each of these. So I want the table of values for f of x is equal to -x squared. I want the table of values for g of x. And I'm just using -2, -1, 0, 1, and 2 for all of these. And then I want you guys to graph h of x. So on your graph, you're doing one at a time. And I want you guys to accurately graph these. And tell me what happens. So what we're doing is we're actually diving into parameter A. Parameter A is attached to the x squared. It's like the coefficient on the x squared. And we're just looking at different parameter A's. So I want you guys to come up with a table of values for f of x with the negative sign in front of the x squared. Another way of writing this guy would be f of x is equal to -1 times x squared, like the coefficient is a -1. I want you guys to graph all three of them on the same grid. Using your graphing technology, give yourself the ordered pairs that correspond with the table of values I've presented with. What did you get for the y value right here? Let's just make sure you guys are all on the right one. -4. Do you guys understand why it's -4? If you had -1 times -2 squared, do you guys see that -2 squared would be +4? +4 times -1 would turn it into -4. Try to think about why your calculator is giving you the numbers that it's giving you. And because there's multiple functions going on to the same, make sure you label it accordingly. F of x needs to be labeled, g of x needs to be labeled. Maybe you want to start bringing different highlighters to class or different colored markers, so when you have different graphs on the same grid, you're going to make sure that you have like a distinguishing feature. Guys, what does the negative sign of the A value do? What did it do? Tell me what the A value did when it's negative. Yeah, the A value is like the number that's attached to the front of the x squared. So what we're doing is we're actually exploring different A values that are attached to the front of the x squared. What happened when the A value was negative? Yeah, so basically your parabola went from opening up to opening down. What math language do you use to describe that change? How do you describe that change? So if we're opening up and then we're opening down, we would describe that as a reflection across the x-axis. You guys see that? So it's reflection across the x-axis dx. So what does the parameter, if A is greater than 0, okay, so if you have a number attached by multiplication to the front of the x squared, like a coefficient, if A is greater than 0, the parabola opens up and has a minimum vertex. Now, vertex is that like turning point. Now, if you look at all of these, with all these negative A's, we're going up and then we're going down. This is the vertex. And as soon as we're like opening down, we have a maximum vertex. So we're just going to learn. So the parabola opens up and has a minimum vertex. That's if the A value is positive. So if we're opening up, okay, that's what it's going to be described as. Next year, instead of saying opening up, opening down, I'm going to say what's the end behavior. And you're going to say it started in quadrant 2 and it finished in quadrant 1. Okay, so if your A value is positive, so I'm just going to put that little note in here. End behavior, Q2 to Q1. So that's if it's opening up. So the parabola opens up and has a minimum vertex. The end behavior is Q2 to Q1. And then we're going to make one comment about the range. Your range is going to be y such that y is greater than or equal to the minimum y value of vertex. And then y is an element of the real number system. So range is always connected to y's. Your turning point will always be your maximum or minimum value. So your range, can you guys read that? Do you want me to like write it bigger? Here, I'll fix it because I can see people squinting at it. Okay, so what's going to happen? If your parabola is opening up, and your vertex is going to move all over the place. So I'm not going to say greater than or equal to 0 because we've only started to explore the first little detail here. Your range is going to be y such that y is greater than or equal to the minimum y value of vertex, and then comma, y is an element of the real number system. You're going to use the greater than or equal to symbol. This symbol is always going to be used when a is greater than 0. You're going to say y is greater than or equal to, because it's going to get up. It's going to go up from there. You're going to have a minimum value. Okay, so we're just kind of exploring details. Now, if a is less than 0, we have to give a description about that first. If a is less than 0, we describe it as a reflection across the x-axis. If a is less than 0, you don't just say it opens down. You say your parabola is reflected across the x-axis. And the result of that, so once you reflect across the x-axis, you would say parabola. Okay, sorry. Did I just throw a word out that you guys knew? I had no idea what I was talking about? The curve shape of a quadratic function is called a parabola. Just like a line is a linear function, so the curved shape is called a parabola. I don't think I actually told you guys that yet, did I? Okay, it's in the notes, it's coming, but just know that when I say parabola, it's just the quadratic function, the shape of the quadratic function. So parabola opens down, and if it opens down, the vertex is going to be a maximum. So it opens down and has a maximum vertex. Next year, we're going to describe it as Q3 to Q4. So if you think about your end behavior, okay, so this guy, this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. You start in quadrant 3 and you finish in quadrant 4. So that's the language we'd use next year, would be end behavior. Okay, so I'm going to say end behavior. Q3 to Q4, and we read it left to right. Now, if my parabola is opening down, let's think about the range here. Let's look at these guys up here. My domain for all of these guys is still x such that x is an element of the real number system. There's no restrictions on x. X gets to keep going forever. But when I look at this, if I'm coming up with my range for this guy, my highest y value is 0 this time. And how I write that, so if my highest y value is 0, my range will be y such that y is less than or equal to 0. Y is an element of the real number system. And so we want to go basically from negative infinity, and our maximum is the 0. So we say y is less than or equal to 0. You would never say 0 is greater than or equal to y. You would state the variable first. So if we have a negative a value, so this is stuff we're going to have memorized, probably within, by your quiz you're going to have this memorized. when you're coming up with your range, because it was a maximum, your range, if you want to memorize it, will be y such that y is less than or equal to the max y value of the vertex. The vertex is your turning point, and then you say y is an element of the real number system. The a value does not change your domain. Your domain is just XCR, and it stays XCR. So just by graphing those functions and looking at the sign of the a value, we get a lot of information. If the a is positive, we open up range, y is greater than or equal to whatever the minimum y value is. If the a is negative, we open down, range is going to be y is less than or equal to the maximum y value of the vertex. Now this part right here, so the sign on the a value talks about whether it's a reflection or not. If it's positive, you would not describe it as a reflection. There is no reflection if a is positive. If a is negative, we describe the reflection. But the absolute value of a, if a has a magnitude, it actually changes the shape of the graph. It makes it narrower or wider. This is, so I would describe this as a vertical stretch by a factor of, guys, what is the absolute value bar? Like, what is this is absolute value of a? What does that mean? You guys ever seen absolute value before? The absolute value of -3 is 3. The absolute value of 3 is 3. It's basically magnitude without direction. So if your a value is -2, the absolute value of -2 would just be 2. We just want to know that it's like a scalar, not a vector. Does that make sense when I say, who's taking physics 20? So you should know scalars and vectors. Scalars don't have direction. Vectors have direction, right? Absolute value is like your physics way of saying scalar, not a vector. No direction at it. So when I say the absolute value of a, so I would say a vertical stretch by a factor of the absolute. The negative sign does something different. If you have a negative sign, it's a reflection. If you don't have a negative sign, you would not say reflection at all. But it's just the absolute value of a just means the negative sign does something different. The magnitude of a gives us our vertical stretch. So it's a vertical stretch by a factor of the absolute value of a, and you have to say from the x-axis. Okay, so I'm going to try to put the pieces together for you really quickly. Okay? If this is my base function, okay, quadratic function in its most basic form, it's right here. This is f of x equals x squared. Oh, not supposed to be right at the origin. That's just a really bad. Okay, the shape that it gives is called the parabola, and the turning point of the parabola is called the vertex. My vertex is sitting at 0 and 0. Are you guys okay with that? So, if I gave you this, hey, g of x is equal to negative x squared. What would the negative sign tell you to do to the parabola? Open it down. We have a negative leading coefficient. So this parabola gets reflected across the x-axis. And we would describe that as a reflection across the x-axis. As soon as you go from this to this, your end behavior changes because you went from Q2 to Q1. Now we're Q3 to Q4. Did you guys see that? End behavior. Domain is XCR, still stays the same, but your range changes. Our range went from y is greater than or equal to 0 to y is less than or equal to 0. Do you guys see that reflection across the x-axis? Okay, so same idea again. Here's your base function. If I said g of x, I'll use a different color. If I said g of x is equal to 3x squared, okay? This would be described as a vertical stretch by a factor of 3 from the x-axis. If I'm pulling something 3 times further away from the x-axis, is that going to make the parabola look skinnier or fatter? It's going to look skinnier. Can you guys visibly see that this didn't get reflected across the x-axis? We're pulling away from the x-axis. So this little ordered pair that was -1 and 1 is now going to become -1 and 3. And your parabola, it triples the distance from the x-axis. And so I would describe this as a vertical stretch by a factor of 3 from the x-axis. We're pulling it away from the x-axis. We're tripling that distance, and it gets way skinnier. Can you guys get your heads wrapped around that a little bit? Okay. Now, what if I had said g of x? There's two things happening now. Do you guys see that there's two things? The negative sign is doing something, and then the magnitude of negative 3 is doing something. What's the magnitude of negative 3, or the absolute value of negative 3? Would be positive 3. So if I wanted to graph negative 3x squared, well, this is what 3x squared looks like. It got narrower. But if it's negative 3x squared, I would have to make it narrower, and I'd have to reflect it across the x-axis. So when you're approaching and you're thinking about the description, so we started with f of x is equal to x squared, and we're turning it into this guy. I would say, okay, what happened to this guy to get this? This is the language of transformations that you have to use. You would say reflect across x-axis. And then you would say vertical stretch by a factor of 3 from the x-axis, and that makes it look skinnier. And I don't think I did a very good job of making it look skinnier, but you guys would make it look skinnier. Can you guys get your heads wrapped around it? So we have our most basic function, and in grade 10 you guys explored the most basic linear function, which was y equals x, and you guys played with slope, and you played with y-intercept, and you added numbers. We're just adding numbers to our most basic parabola. Okay, go to the whiteboards. Okay guys, we're going to carry on. We're going to learn about parameter q now. Okay, so we've already learned about parameter a. Parameter a is attached by multiplication to the front of the x squared. It's like the coefficient on the x squared. But now there's going to be like a parameter q that's going to be outside the squared function, and it's going to be attached by addition or subtraction. So we're going to talk about parameter q. So we've graphed this guy numerous times before. F of x is equal to x squared. Here's your most basic table of values. -2, -1, 0, 1, and 2. And I've got 4, 1, 0, 1, and 4. And when I plot this, and some people don't need the table of values. Some people can go straight to the graph, but would we do that on a written response question? No, we're not skipping steps for written response. If I can't naturally see the flow of your work, I can't justifiably give you the marks for it. Doesn't matter if you have the answers alone, 0 marks for Alberta Learning. Work to justify the answer that you get is where it matters. So here's your f of x is equal to x squared. Now what I want you guys to do is I want you guys to graph g of x and give me the table of values for your g of x. And then graph your h of x and give me the table of values for your h of x. You can use your graphing technology. You don't have to do it in your head. Like using your graphing technology, let's just double check. Do you have this table of values? When you typed in, like y2 is equal to x squared plus 4, did you get -2 and 8, -1 and 5, 0 and 4, 1 and 5, 2 and 8? totally change the whole position of the vertex. Do you guys see that? Like, if you were looking at your g of x, what would your range be of your g of x? Do you guys see that your range would be y is greater than or equal to 4 this time? Do you guys see that? Okay. How would you describe from f of x to g of x? Did the shape of the graph actually change? Did the width of it change? Like, did it actually... In junior high, I used to call this a slide. You guys remember talking about slides? Like you would transform a graph by sliding left 2, up 5, or something like that. You'd call it a slide. We're going to describe this as a vertical translation. So you got to learn the real language. This would be considered a vertical translation up 4 units. We picked up the whole graph and we moved the whole thing up 4 units. Would you guys say that that's a legit way of describing that? Now, when you graphed x squared minus 3, did you guys get those ordered pairs? Like -2 and 1? If you actually look, every ordered pair was just moved down 3 units. The shape of the graph did not change, and I need to be taking it right to the edges. So this is my h of x. Guys, what's the range of my h of x? Okay, let's just do a quick range. What would the range be here? Y such that greater than or equal to what value? -3. It's the y value of the vertex, and then we say y is an element of the real number system. So the range actually changed. The y value of the vertex actually changed. We went down 3 units. When I look at this guy right here, my g of x range for g of x was y such that y is greater than or equal to, my lowest point was my y value of my vertex, so it's 4, and then y is an element of the real number system. So the q value just either picks it up or moves it up or down, and we call that, what you call the slide in junior high is just going to be a vertical translation. Okay, so guys, do you recognize that this is just describing a positive number? When you see q is greater than 0, you're thinking positive number. How many of you guys just referred to these as like the crocodile mouth opens to the left, crocodile mouth opens to the bigger number? Like, did you guys actually learn how to read them properly, or did you just see them as crocodile mouths that open to the bigger number? Crocodile mouth. Totally a crocodile mouth. This just means if q is greater than 0, this just means it's a positive number. If your q is greater than 0, if it's a positive number, you're going to describe it as a vertical translation up, and then you would say q units. So it just picked up the whole crowd. If it's positive, it goes up. If it's negative, it goes down. Okay? When you see q less than 0, you're thinking it's got to be a negative number. And maybe I should have talked about that with the a's. When it said a was greater than 0, you're thinking it's a positive a. If a is less than 0, it's a negative a. Okay? So if your q is negative, so right here, we had a negative q value, -3. Maybe I should have color-coded that. I would describe that as a vertical translation down q units. This is the first time I really introduced you to a lot of the language of pre-calculus. Like, you guys are going to have to use the language of pre-calculus. Now, last one, and then we're going to put all the details together. We're going to look at parameter p, and the reason why, this is vertex form of a quadratic. Okay, this is what we're diving into. A bracket x minus p squared plus q. They told us two things. If A was negative, we'd have a reflection across the x-axis. If A was positive, we stay opening up, right? If A was a number, we'd have a vertical stretch by a factor of A. And then we said Q is going to move the parabola up or down. Okay? The Q value is going to be the Y value of your vertex. Now we have to dive into P. So what I want you guys to do is you've got f of x, you've got g of x, and you've got h of x. This time you're going to have to adjust your table of values slightly. And I'm going to give you guys the x values and y values that I want. So this one is standard. This one I want you to choose these x values. And when you look at the graph, you're going to understand why. All I want you guys to do is graphing them one at a time, create a table of values for each function, sketch all three of them on the same grid, and then we're going to talk about them. Guys, what do you think parameter P is? How would you describe? Okay, so parameter P is actually directly attached to the x inside brackets, and then that function gets squared. So this was x plus 3, close the bracket squared, but then we ended up getting this red graph. How would you describe from f of x to g of x? What happened? Junior high would have said slide left 3. You guys see it as a slide left 3? In pre-calculus, we describe it as a horizontal translation left 3. And it's the exact opposite of what you'd expect. That's why you get this negative sign in here. Sorry, I have a typo here. This was supposed to be an F right there. So you're given a negative sign in here, and you'd almost expect that this should be right 3, but it's the exact opposite. It's the inverse operation. It ended up going left 3. So when you think about this guy right here, the vertex was moved left 3. When I look at this guy right here, this one was moved right 2. And it's the exact opposite of what you'd expect to see happening within the bracket. Okay? Domain, XER, range, y is greater than or equal to 0 for all of them. The y values didn't change. The only thing that happened was the vertex was moved horizontally. So, when you're thinking about this, when you see this in brackets, the p-value in brackets, I need you guys to think horizontal translation right. And it's the exact, so if you see a negative sign, so if you see that it's negative, it's going to the right, p units. So if in brackets you see a subtraction sign, you're going to the right. If you see an addition sign in the brackets, you would describe it as a horizontal translation left p units. And what that does is it changes the x value of your vertex. It moves it right or left. So this is your big concept map. You've actually been introduced to like 4 transformations right now. And this is the equation that you get on your formula sheet. So this is called vertex form of a quadratic function. And it says the parameter A gives the direction of the opening and the vertical stretch factor. So it's a vertical stretch by a factor of blank from the x-axis. So if I had like this, y is equal to -2, x minus 3 squared plus 4. So if I had this function as my example, actually, you know what, I'll just put it right here. Here's my example. Y equals -2x minus 3 squared plus 4. From your most basic quadratic function, I would describe that as a vertical stretch by a factor of 2 from the x-axis. Like the 2 is telling you that it's going to get narrower. Can you guys actually see that? Is that better? Now, if a is greater than 0, you'd say your parabola opens up. It has a minimum value, and the range will be written y such that y is greater than or equal to minimum y value of the vertex. Now, if a is less than 0, you have to give this description. You have to say, oh, there was also a reflection across the x-axis. What that does is it changes your parabola from looking like this to looking like this. Now, this x minus p means you're going to the right p units. This x plus p means you're going to the left p units. And then plus q means you're going up q. Down q means you're going down q. So when I look at this, this is telling me that my vertex is moved to the right 3 and up 4. So my vertex, my turning point, is actually positive 3 and 4. And then I know my parabola is opening down from there. Do you guys see that? So this p-value is telling you take your vertex, move it to the right 3, take your vertex, move it up 4. This is now your vertex. Usually your vertex was sitting at 0 and 0, right? Now this is going to tell you horizontal translation right 3, vertical translation up 4. This is your new vertex. This is what you need to know. So everything 3.1 is going to be on your quiz on Thursday. 1.5, infinite sum, is going to be on your quiz on Thursday. Okay, so keep that in mind. So what do we know? The vertex is always going to be your P and Q. So it's the exact opposite of what you see here for P. So you always take the exact opposite. Now every parabola has something called an axis of symmetry. So when you look at this parabola, when I approached this function, I knew it was going to open down because it was a negative a value. Like I knew that there was a reflection across the x-axis. And then I would say, oh, there's a vertical stretch by a factor of 2. So my parabola is actually a little bit skinnier than a normal parabola, like a regular parabola. And then this is telling me horizontal translation right 3, vertical translation down 1. So usually I'm sitting at the origin 0 and 0, but I have to go right 3 down 1. And because a is negative, I would open my parabola down from there. That's what f of x is. And you guys should know what every single number does to make this parabola shape happen. Your vertex was at positive 3 and negative 1. So I'm going to write that right here, 3 and negative 1. Because a, and it's a maximum, and the reason why it's a maximum is because a was less than 0. And as soon as a is less than 0, we have a reflection across the x-axis, making it a maximum. Now, something you haven't seen yet is an axis of symmetry. Parabolas are always symmetrical about the vertex, okay? This vertical line that cuts this parabola in half, every vertical line is depicted as x equals. This is called your axis of symmetry, and it cuts your parabola in half. If you were to fold your parabola on the line x equals 3, it would land on top of itself. So every parabola is symmetrical about an axis of symmetry, and your axis of symmetry is always the x value of the vertex. So that's what you're going to grab. It's always the x value of the vertex. So we would write it as x equals 3. That's your axis of symmetry. I know that my a value is less than 0. That means it's negative. My domain is x such that x is an element of the real number system. My range is y such that y is less than or equal to, what's my highest y value? Negative 1, right? It's less than or equal to because my a value is negative, and then I say y is an element of the real number system. So ultimately, by the end of this course, you want to be able to look at a parabola, actually at the end of this unit, and you should know exactly what it looks like without even typing it into your calculator. That's your goal. You're going to be able to algebraically determine x-intercepts. You're going to algebraically determine the vertex. You're going to know how to sketch this guy. So this is vertex form because it actually gives you the vertex. This here is telling you left 1, down 2. So if I go left 1, down 2, I'm going to go from 0 and 0. If I go left 1, down 2, there's my new vertex, negative 1, negative 2. It's the exact opposite of what you see in here, and it's the direct Q value. So vertex is negative 1, negative 2. Your axis of symmetry is the vertical line that cuts your parabola in half. And we would have x equals negative 1. It's always the x value of your vertex. If you got your vertex, everything else falls into place. X equals negative 1. You can't just say negative 1, because it could have been y equals negative 1. It could have just been a negative 1. You have to give me that vertical line. Now, a is greater than 0, so we know it's opening up. Your domain remains x such that x is an element of the real number system. Your range is y such that y is greater than or equal to the lowest y value. We're going up from there. For the first while, you're going to be typing these graphs into the calculator and you're going to look at them. Then eventually you're going to look at the equation. You're going to know exactly where that graph should land. Okay? So just think about, don't worry about compressed. We don't use that language anymore. It's a vertical stretch. So just say, I will ditch this, because that's not the language you use anymore. Okay, the textbook might use that, but don't worry about it. If A is positive, the graph opens up and has a minimum value. If A is negative, the graph opens down and has a maximum value. And don't worry about the other numbers. We won't talk about compression or stretches. Okay? Can I get you guys just to pack up now? Because that's all we're going to do.
Are you 7 drawn here?